Good afternoon, and welcome to the tutorial on OpenML. You may have noticed that the network is down, which will be a problem because we have lots of practicals prepared for you that require the network. Hopefully it will come back over the coming 30 minutes or so. If not, everything that we'll present, you can also try at home. And the slides and everything that you need is available online on GitHub. There's a short URL there on the screen. If you have not taken it, written it down or taken a picture, do it now, then you can later also find it. Okay. Cool. Not yet. All right, so welcome again. I'm Joaquin van Schoren, this is Berend Bischel, and this is Heidi Seibold. And together we're here to present OpenML and the R package that allows you to use OpenML from any R script. So to start, you will need an account on OpenML. So there's a website called openml.org. To do all the exercises, you need to go there and create an account. You also need to verify your account in your email. And you also need to install two packages. One is OpenML. You can just install it from cron. And also a package called farf or fastarf. That's to read ARF data files. Right? If you have any problem during the tutorial that's not related to the network, you can ask one of these post-its. You can either put them on your head or somewhere you can see it. And then we will come and help you. Yeah, the tutorial is available there. We'll also put a link on the homepage of OpenML and also in the useR guidelines.
Does everyone have a post-it note? No. They should be somewhere, and you just have to pass them around.
All right.
And also, does everyone have a cheat sheet? Just keep up your hands and up front of you.
Awesome.
Problem is if we don't recover from the network problems, we have like zero chance of you really taking part in the practicals because you need to be online for some of the stuff, or like to get the stuff started at least. Yeah.
Do you have a connection?
We have zero connection.
Is it worth everyone just turning off our connection?
Possibly, that's possibly an idea. The thing is, I also tried the cable connection, even that doesn't work. Yeah.
My connection is back now.
Back?
It's back. I'm on your slides.
Great. Yeah, I'm getting something on mine now as well. It's just super slow, but it's at least resolving.
It's working.
Great. So don't work all at the same time.
Right, cool. Let's start. Okay, so OpenML is a platform for machine learning where you can share data sets, you can share workflows, algorithms, and you can also download them. You can share machine learning models and download them. So it's basically a platform where you can collaborate to build the best machine learning models together. Why we do this is because we want to inspire and empower everybody to do great machine learning. That means find interesting data sets very easily and use them immediately. Import them very easily into your code. You can also share your own data sets if you have interesting data and you want to collaborate with other people on it. You can also view the problems that people are working on, like classification problems or regression problems that people try to tackle. You can join them in solving that problem, or you can also crowdsource your own problem. You can share a problem with other people, invite other people to help you, or just reach out for people to come and help you solve that problem. You can use open source tools to try many algorithms to tackle these issues. You can use, of course, R. You can also use Python or Java-based frameworks like Weka. And you can use these tools by just having a plugin or an API to download data sets, to build your models and upload the results back again, very easily in a few lines of code. And we will see in this tutorial how this works exactly. And what we also do is we try to automate all the drudge work, it's also called AutoML. We create smart robots that help you decide which models, which algorithms are likely to work well. And even if you just upload data sets in OpenML, there will be robots building models on your data sets. And these robots, they're smart because they learn basically from all the models and experiments that people share in OpenML. It learns across all these experiments to build the best models. OpenML is designed to make all the results that you share automatically reproducible, transparent, and reusable. So when we upload a model or an experiment from your R script, we make sure that there's all the metadata available that other people need to reproduce your experiments. So everything you upload to OpenML is reproducible. And it's also organized all together, so you can easily browse through the entire community's experiments to find the interesting models for you to work with. And we want to create frictionless collaboration to make it very easy to share your data and results and do your work much more easily. Right? So how does it work? Imagine you have a data set and you want to ask a few people that you know to build models on these data sets. You can then, of course, share them on OpenML. Other people can then download them, and very easily, in a few lines of code, they can build models on the data set and automatically share those results back to you. And you can then look how well they perform. You can also do this on a web scale. You can have a data set and share with many people all over the world, invite anybody to build the best models on those data sets, the best scripts to analyze the data sets, and then share the results back to you. That means the models, the visualizations, the code. And then you can compare all these submissions and see which ones are the best. The other way around, if you have a new algorithm, you can browse OpenML for all kinds of data sets, easily import many of them, and automatically run your algorithm on all these data sets, which is for benchmarking, and you will see when your algorithm performs very well and when it doesn't. And you can do this completely in real time, right? So you can write scripts, it's completely scriptable. You can write scripts that just listen for new data sets, download them, run algorithms, and upload the models automatically, right? So you can completely do this in real time, and you don't have to wait for an experiment to finish and then email it to somebody. You just add one line of code at the end of your script that automatically uploads your models to the person you want to share it with, or just with everybody. It's an open science platform, and to make that work, first of all, we want to make it very easy to use, and that's why we integrated right into R tools. So you can use, if you use R, it's very easy to use OpenML. It's very easy to contribute. You can contribute a single data set or a single experiment. Everything is organized, so you can, if you share an experiment on your algorithm, you can immediately compare how well your algorithm performs to anybody else's algorithms, and you can easily search and download other people's results and data. And there's a reward structure, because if you share data or algorithms or models, you can see how often people are reusing your contributions. And that tells you that you're having impact on the field. And finally, OpenML is self-learning, so over time it learns from all these experiments to help you build new experiments, to build better models, right? So we will show some examples at the end where OpenML can help you decide which algorithms to choose, which parameters you choose, which ranges of parameters are likely to work well, based on all the information OpenML is learning from. Okay, so how to use OpenML? Typically it starts with data. The data can live anywhere, so it can live on your Figshare account or on Zenodo or wherever you want. And you can just tell OpenML the URL. If you want, you can also upload data to OpenML. but it's fine to just give a URL. OpenML will then download your data set and automatically analyze it if it understands the format. And then we'll create a web page for this data set that's automatically created. And there we bring together a whole bunch of metadata about your data set that's automatically extracted. For instance, a breakdown of the features if it's tabular data. It also computes properties like how many observations are there, how many missing values, how many features, and so on. This is all automatically extracted and organized online. You can then create a task. And a task basically tells people what you want to do with your data. A typical case is that you want, for instance, to do classification. You want to predict a certain target. And a task is something you create online, and then other people know what you want to do. And more importantly, this is machine readable. So you can write automatic scripts that look at many different tasks and try to solve them automatically. And all the results that people share about this task are organized online. Here's a timeline. You see all the colors of different people, and all the dots here are models. So you can see how different people are building different models. The higher, in this case, the better. And this is all open. So you can, at any time, you can look at a task. You can see who is building the best models. You can see which models are working well. You can click on them, see what people are doing exactly, and you can try to improve upon that. So you can learn basically based on anybody that anybody is running an OpenML. To build models, so to run your own code, you can use any of these tools. We provide libraries or plugins or interfaces for all these languages. I'm going to focus on R now. So these are just 4 lines of code that at the end of this tutorial you will know very well. First of all, we download a task from OpenML, and that includes also the data. Then you can use, for instance, the MLR library to build a classifier. You can then use runTaskMLR to run this task, to run this learner on this task, and then you will get a model and results, and then you can upload it to the system. And when you upload it, OpenML makes sure that all the metadata that you need, like the versioning of all the libraries that you're using, the exact data sets that you and the exact data set versions that you're using, the models if possible, and also the evaluations of your models are uploaded to OpenML. And OpenML will then evaluate all these models based on the predictions, and so you have a complete overview of how well different algorithms perform. And this is linked to the people, to the data, to the flow, so you know exactly what's been going on and you can reproduce it. And again, every run gets a web page where you can download, for instance, the code and the models, and you also get a breakdown, a very detailed breakdown of all the predictions. And everything I'm talking about is open source, so you can download all the predictions. It's all publicly accessible. You can download the data, you can download the metadata. You can use it for whatever you want. We also keep profiles, so you can see how active people are, and if you're very active, people will also see this. Let me risk giving a demo, giving the network. So if you go to OpenML, you basically see this. So you see we have about 20,000 data sets, about 40,000 tasks, about 4,000 flows, and almost 4 million models, runs. So runs are algorithms run on a task, and these either include a model or a model plus evaluations of that model. Let's take a look at the data set. So if you click this, and there's a network, and there's not one today, but okay. So what you should see here is a long list of data sets. You can click on the data set. You can then see which tasks there are. You can see how well different models perform, and so on. Very sorry about this, so please try this at home. Yeah.
Can you explain what's the task is?
What task? Yeah.
What's the type of tasks are?
So the type of tasks that we have right now are things like classification, regression. We have a learning curve analysis. We have time series analysis. Survival analysis. We're starting with clustering also. And this is, if you work on different tasks that not yet supported, you can always contact us, and we will build new tasks for you.
So you have like a set of predefined tasks that you
Yeah.
have to choose from.
Yeah, so typical case, like you have a data set, for instance, and you want to do regression with it, you create a regression task where you say which is the target feature that you want to predict. You say which is the evaluation measure that you want to use to evaluate any model that's being built on it. And OpenML will also create trained test splits, so you already get those, you can compare results.
It's basically the data set, a reference to the data set, predefined resampling splits, so cross-validation splits, and potentially a measure you want to optimize that you can also leave out.
So the driver, the platform takes care of the defining possible validation.
Yes, you can upload custom splits. So if you have a really predefined trained test split, you can upload this, but if not, you can also auto-generate a 10-for cross-validation that then everybody has to use.
Right, but like, you know, how do you compare against other, if they are not using the same validation set?
So within a task, everybody uses the same trained test splits. So you choose, for instance, I want to use 10-fold cross-validation. OpenML will then create trained test splits. And if you download the task, it also includes the trained test splits so that everybody uses the same splits. And you can compare results. Yes? Oh yeah, sorry. The question was, sorry. The next question is, what's the limitation on dataset size? There is, if you want to upload new datasets to our server, I think that's probably a 4 gigabytes limitation there. But you don't have to upload anything if you don't want to. You can put your dataset wherever you want, for instance on Amazon, and just provide the link to us. And we will download it and extract metadata from that. But you can, big data sets are better left where they're put right now. Yeah.
So the limitation would mainly exist locally, yeah? If you want to work with this and download this, yeah?
All right. Cool. All right, so let's dive into the tutorial, if we can make this work. Any more questions at this point? No?
So I would suggest if the network problems stay, just ask many questions. So we will use the time for that. I think that's the only thing we can do.
I tried to delete something.
Yeah.
The data set because I missed it.
Everything that's yours, you can delete. Right now we still have an issue with cascading problems. So if somebody else builds on your data set and you're then there's some, but normally if you have ownership of your data sets. Yeah.
So there are a couple of things. I mean, when you maybe want to delete stuff, I mean, maybe because stuff is faulty, right? Yeah. You can also report problems. You can flag stuff. So if stuff just looks suspicious and you're not really sure, you can flag that and people can check and you can comment. You can delete stuff that belongs to you, but at a certain point, if stuff really becomes kind of officially integrated into studies, we will not do this. So if like permanent links refer to this, we will not, because otherwise stuff will not be reproducible, right? But if you upload stuff and it belongs to you and nobody has done anything with it, you can.
Yeah, it's just making error.
Yes.
Exactly.
I just wanted to mention because errors in these, I mean, large-scale projects occur at every point. You can also flag stuff of other people and report stuff where you think it looks suspicious.
Cool. Okay. So now let's dive into the tutorial. So yeah, to use OpenML, all you need to do is to install the OpenML package and then import the library. Then you need an API key. An API key is just a string of characters that uniquely identifies you. If you want to find it, you log into OpenML, you go to your account, and you click here on API authentication. There you find your API key, and you can copy-paste that into your code. The way you do that, because you don't want to keep this into your code all the time, what we do is we automatically create a little file on your hard drive, just a plain text file, and you can use R using the same OML config method to store your API key. You have to do this once, and then it's stored on your machine, and you have to don't worry about anything again. Right? There's some other configuration options that you have. You can choose a server, although right now it's best to use the domain server unless you go into development work. There's a cache directory, so OpenML will, if you download data sets, you don't want to do this over and over again. So OpenML keeps a cache of everything that you download, and you can choose where this cache directory resides. You can choose verbosity, you can use an ARF reader to read ARF data, and you can choose whether or not you want to have a confirmation box when you upload stuff to the server. Okay. At any time when you're wondering what your configuration is, you can just type get oml config and you get a full list of what's in that configuration file. Okay. So for the practical, the idea was that you install the package. I'm very hopeful, but this won't work. So yeah, please try it at home. It's basically just 2 lines of code to set it up. Okay. Then you can list all the OpenML data sets, right? So you have a command called list OML data sets that gives you basically the whole list of data sets known to OpenML. This is metadata, right? So it contains descriptions of those data sets, a textual description about what the data set is about, a URL where you can download it, and so on. It's paginated, so you don't stress too much your network. So you can download 5,000 results at a time. And this includes things like the name of the data set, the versioning, and so on. This is a small slice of the data frame. So here you see the different data sets. They have names like anneal and labor and arrhythmia. These are all from UCI, but we have many, many more. And you also get some metadata. For instance, here we just show the number of features and the number of instances. You can also list tasks the same way. So you just use list OML tasks. You get a list of all the tasks. For each task, you can see what the task is about. For instance, the first task is about supervised classification on dataset anneal, using tenfold cross-validation and using predictive accuracy as a target. Right? These are all classification tasks. Right? If you want to see the task for a specific dataset, you can just include the dataset name as a filter. And now you see only the tasks for this data set. And here we have 1 clustering task defined and 2 classification tasks. They both use tenfold cross-validation, but the one optimizes area under the rock curve, the other one optimizes predictive accuracy. Right. That's clear? Okay. Flows, these are algorithms that you use to solve these tasks. You can also list them with list OML flows. Here you see a small slice. These are all Weka algorithms, but these can also be R algorithms or Python algorithms or Java algorithms. Right? There's also XGBoost, there's also H2O is also possible, and so on. If you then want to see which runs, so before I now have a specific task for this gesture face recognition, right? So it's a data set about recognizing gestures and people's hand movements based on accelerometer data. So now you want to see, okay, what has been done on this data set. If you have the task ID, you can now ask for all the runs on this task. And here you can see there are a couple of runs people have been running on this task. And if you want to see how well they perform, you can use list OML run evaluations to get a breakdown of which algorithm was used and how well it performed. And then we have another practical. So yeah, again, please try it at home. We have the solutions here. So you can easily do this at home, and if you get stuck, you can peek at the answers. We can go through solutions, yeah. Yeah, we have enough time. So first of all, the question was, so give me all data sets that have between 100 and 200,000 observations, but are very low dimensional, less than 5 features, less or equal than 5. So for that, we just use list OML data sets with 2 filters. The number of instances should be between 100,000 and 200,000, and the number of features should be between 1 and 5. That's basically everything. And then you get a list of all the data sets that match these requirements. Yeah. So you can easily browse the entire OpenML ecosystem for data sets that fit your needs. Right? You can also ask for things like, give me data sets with or without missing values, with extreme class imbalances, for instance, all that stuff you can ask for. Second question, very specifically, you want to have tasks, regression tasks, that have between 50 and 55 observations, right? Very small window. But you see there are quite a few data sets that match these requirements. And just by setting, so here we filter by the task type, so we only want regression tasks, and those tasks should have between 50 and 55 instances, and you get those back. Just 2 filters. Next, you want to find the data set gesture face recognition. So for that, we just list the data sets, and we use the data set name as a filter, and now we get only one result back, and we see, okay, this is data set number 4537. It's in the R format. It has about 3,000. So the majority class is 3,000, the minority class only 1, and so on. 6 classes, and 20 features. Finally, we want to see what's the predictive accuracy for all the evaluations on this task. So we just call list OML run evaluations with the task ID as a filter, and we get all the models that have been built here with their respective performance. So OpenML computes over 30 different performance metrics. Here we show area on the ROC curve, cost measure, and kappa, and so on. But you can get any of this data you can back. So if you want to know which is the best model for this task, you can easily get all the data back. Yeah, there was listing stuff. You can also download items. So first thing you can do is to download a data set. For that, we have the get OML dataset function. We give it the ID of the data set, and what you get back is a data frame with the description of the data set. So it has a textual description with information about, okay, who created it, what's in this data set. And it also includes the data itself, so the numbers. By just asking for the data attribute here, you can get the full data back. Right? So that's just one line of code, and you get a data set from OpenML, and you pull it into your script. You can also download on datasets by names. Say you want to have Iris once again, you can get OML dataset. Data name is Iris, and you will get Iris into your script. You can also download tasks the same way. You give the task ID, and you get, again, the full description of this task. This also includes the data that's attached to this task. And you can do the same thing for flows. So here we have one specific flow, number 100. This turns out to be a Weka algorithm, J48. And you can see the version. And the same thing with runs. Just by giving the run ID, you get all the information back about this run, and so on. Any more questions here? So it's super simple. You get data sets, you get tasks, you get runs, and your evaluations. Yeah? A flow is, depends on the toolbox. So if it's MLR, for instance, or most R libraries, it's a description of the algorithm that you're using, or it can also be a workflow or a pipeline. Right? If it's Python, you get a Python pipeline, and the next thing that we're working on is to also allow scripts. So you can have the flow can be a full script in R that you upload. But right now it's basically a description of the algorithm that you're using. Want to say something?
I was told that if I add things, I have to speak into the microphone. So the idea of the flow is just to upload as much meta information as you can about the pipeline you're running on the data set, yeah? I mean, on the most basic level, that can, I don't know, be a decision tree. And then you upload all of the hyperparameter settings and what you know about the tree. What you actually the information you would need to reproduce the run locally, yeah? That's in there. and we also upload binary representations, serializations of the pipelines, so you could also really automatically reproduce this. Yeah, but the flow mainly contains, well, the main parts of the flow are descriptions of what happens in the algorithm.
So that's something you need to define, like you basically craft the flow and upload it.
No. And so the question was, do you need to, I don't know, does this create some extra hassle on your side? Do you need to define this? And the answer is, you could basically call a constructor from the R package and enter all of that information manually. But this is really, really tedious. And as you will later see, this is completely auto-extracted, at least from the MLR package at the moment, and for Python and for Vector and so on, because all of these toolboxes know so much about these algorithms that we can auto-extract that. Yeah, you have to do nothing. You basically select what you want to run, and the client package takes care of extracting that information and uploading this. And then this gets converted into the same XML format, right?
Yeah.
For each client. Yeah. So it's the same descriptive XML for R, Python, Java, and so on. The contents just look different.
And it's really tool dependent, so it depends on what you're using and what it allows. If you have a tool that has very deep information about the algorithm, you can upload a lot of information. For instance, in Python, we can actually take a flow and automatically write a script that generates a pipeline. So it depends on the tool. Finally, we do caching. So to limit network traffic, we keep a little folder inside your .openml folder called cache, and there we store all the data sets and flows and runs and tasks. And it has basically this structure where you have a folder data set, and within the folder you have numbered folders for every data set ID, and then you have all the data itself and the metadata about the data set.
So you upload multiple times, you will upload only once.
If you download, so if you download a data set, you download it only once. Data sets in OpenML, they are versioned and they are stable.
No, but is the upload, or this is only for download?
This is for downloading.
This is not for the upload side.
Yeah. This is very useful, for instance, if you want to run on a cluster without internet access. You can also use this populate OML cache. So if you say that you want data sets 1 to 1,000, this will just download 1,000 data sets at a time and store them in your cache. And you can then continue without network access. You can also very easily create a full copy of OpenML this way. Yeah, time for another practical. The solution is very simple. So here we just want to download the task with this task ID. So we just use get OML task, and then we have the task. And then we can do introspection. So we can look at the task. It has an input, the data set. So this is apparently the task about Iris. And we can also look at the data itself. That's also part of the task. And with this, we arrive at the break. Are there any more questions right now? No? Okay. I do implore you to try this at home to see it all work. It's very unfortunate that the network doesn't work right now.
I mean, currently we are kind of twice as fast as we should be, yeah? Because I mean, all of the practicals are, I mean, that usually eats up lots of time that we allocated for. So I'm not sure what we should do now. I mean, one option would be we just go through this in this slot, and then it's just half the time. It's maybe better than breaking now for half an hour as we, right? So we just continue. Is that in your interest? Okay, yeah. Sorry. Really sorry about this bit. I mean, the thing is we cannot do this globally with, I mean, it's the client server thing, right? So shall I just take over and we continue?
Yep, sure.
Yeah, sure. You can, of course, you can ask questions.
How do you search the task if you don't know ID or anything? I mean,
Okay. How does it?
I want to get like 100 dozen of results if I look for a lot of classification or location or whatever. It's not clear to me how you search.
Well, I mean, can you give us kind of a use case, why you are searching stuff. So do you want to, for example, benchmark an algorithm, or do you want to figure out on a domain what's the best? Yeah, so you're kind of, for example, yes, okay, yeah, or you want to, for example, classify high-dimensional stuff, yeah? Then you can just use these lists. I mean, you can list stuff either on the web page, you can even do this through the web GUI, and run the same types of searches. So for example, you can say, well, I want to do classification, it should be binary, I want to have roughly balanced class sizes, and please give me everything that has more than, I don't know, 10K features, yeah? And no MAs because I don't want to deal with imputation. And then you can always have a look at, well, am I getting back 10,000 results, or is it just 3 data sets? And you can either refine or broaden the search. So that would be something, yeah? Another use case might be you are looking for very specific data sets, yeah? For example, I don't know, I'm your colleague, yeah? And I'm uploading these very specific, I don't know, biological data sets that you're interested in. You can also tag stuff, which Heidi will show you later. So maybe I'm just tagging everything with Baron's cool, I don't know, data suite, and then you download just those, and then it's really super easy to search for that.
If you have any questions like this, you can also just type question mark and then the function, so question mark list OpenML tasks, which gives you a full documentation. So you see for tasks here, you can filter on the task type, the estimation procedure like cross-validation, any measure, the number of instances, number of features, number of classes, tags, data set name, and so on.
For example, I'm looking for data set, but on a very specific topic. I don't care how many observation, I don't care how many feature you have, just on a specific topic.
For that, it's best to use the website. So if you go to
So
openml.org.
Maybe let me repeat the question and not forget that. So he was asking if I'm looking for a very, very specific data set, yeah, from a very specific domain. So I'm guessing you could detect whether the data set is the one you want from some terms in the description. Text-based search, right? Yeah.
If you are on the OpenML page, there is a search, very powerful search engine, and then you can search on any topic that you want, and then you will get the tasks back that belong to that.
Yeah, there's a free, correct me if I'm wrong, but there's a free text search over all of the descriptions and all of the objects. Yeah? So that would also work. And maybe to add another answer, so if you're interested in benchmarking stuff because you are, I don't know, developing classification algorithms, or you're just very interested in machine learning in general and comparing algorithms, we are now also creating certain studies. Yeah? So pre-specified suites of data sets where you can compare maybe against the results that I produce, but Heidi will also talk about that. So let me not foreshadow this too much.
I was a little bit reluctant to try your stuff because I didn't want all my test data to be public. It was just playing around. Wouldn't it be possible to do something like a temporary tag on your metadata and say this is valid for 1 day only, and then it will be deleted and it will not be public, because it's well, playing with all this. I don't want to pollute your data.
Yeah, so there's a feature that we're working on right now.
I need to repeat.
Yeah, sorry. The question was, is it possible to basically to play with my data privately on OpenML without anybody seeing it? And deleting it, yes, of course. So I didn't go into it as much, but these are things we're working on right now. So we allow a sharing setting, which will be similar to what Google Docs has. So by default, your data is private, and you can share your data with a number of people or publicly. And then you will only have access to, if you don't want to share data openly, you can keep it to yourself, play around with it, and delete it afterwards if it's not interesting. If it turns out to be interesting, you can then make it public.
Yes, and we are also discussing at the moment, so there are these circles of trust that Joachim just outlined, or where you can keep stuff private because you're not sure whether it really is worthwhile to publish this. And then there might also be, I mean, we really love stuff to be really open as scientists, but we also acknowledge the fact that for, I mean, some communities this will never be the case completely, right? So we are also discussing at the moment having private instances of OpenML where you can access the public database and, well, quote unquote, leech from it and have your stuff
that you really have to keep private just in your group, in your network. Yeah?
But something like an auto delete after 2 days would be okay too. Give it a lifetime and then it's gone. You don't tell this
Yeah.
is just playground.
But if you would just, for example, I mean, the circle of trust for your datasets then, for your temporary datasets, could just be yourself, and then you can also just take the API and wipe it clean, right? That's also possible. But at the moment, this, how you call this a lifespan of a dataset doesn't really exist.
Yes?
To expand on this question, do you see this as a platform for academia research or for more commercial research? Because obviously this commercial data, my company will be mega reluctant to ever release any private information we might have on our customers, right? I'd have to sign 20,000 lawyers, in the company to allow me to put something there. Although I think the idea is great, right? And somebody could improve on my algorithms. And question number 2, how does this compare with Kaggle?
Okay, let me repeat. So correct me if I'm summarizing incorrectly, but your first question was, what's our target audience? Is it academia or companies or both? Yeah. And the second question was, how does it compare to Kaggle? I think you have to answer.
Well, OpenML is meant for everybody. So right now it's very, very open, and that's the groundwork is to keep everything open. Right? If you are a company and you're not even comfortable sharing things in this private way, you can set up your own instance. Right? So all our code is open. You can download OpenML as a web application and then run everything locally and keep everything within your firework. It's a bit more work to set it up, but it's also possible. And for who else is it? This is not only for researchers, it's also for students and for anybody, citizen scientists who want to get into machine learning. So we want to target everybody, and that's also why we want to be as open as possible. But if you really don't, if you can't be, then it's also possible to set it up locally yourself. How is it compared to Kaggle? Is that we are not. We're basically designed to be a collaboration platform and not really a competition platform. Right? So here, everything you do is meant to collaborate, everything is open, and you can see anybody's experiments or anybody that you know and that you trust. You can see his or her experiments. On Kaggle, you only see, I think, the top 1 performer in the challenge, and the data sets also disappear after a while. On OpenML, all data sets will be ever available. All the models are open. You can see all the scripts are open. You can see everything that anybody wants to share. It's completely open.
I think we also extract a lot more meta information. Last time I checked with Kaggle. So all of these different characteristics of the data sets and of the algorithms, I don't think that Kaggle really does that. Much more unstructured, I think, at the moment.
It's just, the basic difference is that OpenML is meant for people to build good models together, and not really a challenge.
So I think, did I hear correctly that like when you upload a data set, that you have some like scripts, like you automatically try some like baseline models? Can you talk a little bit about that?
So I think the question is, if you for instance upload a data set, do we already compute something on the data set?
Yeah, like do you have like models that you automatically try?
Yeah, so we have a series of bots. First one is this OpenML bot. So it currently has done over 1.5 million models autonomously. And this is also one other big difference to Kaggle, is that we keep all this data open so that people can build robots and scripts that have access to the full data that anybody is producing. It's basically a collaborative mind of everybody who does machine learning that you can build upon. And you can build these robots, and you can build ever better robots that do this. So yes, if you upload a data set to OpenML, these bots at some point will come across your data set and automatically build models. And we hope that as we build more and more intelligent ones, and we have quite a few in the pipeline, that these predictions will actually be very good. And
how many of these bots do you have that run?
we have currently one running continuously, and I don't have slides for this. But we have also some other ones. I think let me quickly bring this up. So this is another one that we are writing that actually builds pipelines.
Have you found it?
Yeah. So this is Python. Sorry for that. But this is a script. Basically, what it does, it looks at a task. It does random experimentation. It learns which workflows, and that means combinations of pre-processing steps and models work well. And then it's going to use genetic programming to cross different workflows. And that way it will evolve better and better workflows over time. This is one of the most advanced right now. And if I run this, you can see so every pink line will be a generation. So every generation it builds more complex pipelines. And at the end, it gives you not only a model and good performance, it also gives you the script that builds the optimal model. Yeah. And another thing that we're using that will come back later is hyperparameter tuning. So you have robots that automatically learn from all the hyperparameters that people have tried in OpenML to tell you which hyperparameters are best to tune and which values are most interesting to use.
Yeah. I mean, all of these projects that Joachim just outlined are pretty new and to some extent experimental. So for a longer time it was that you had, if you uploaded something, at least somebody, maybe yourself or maybe I had to download this locally, run something, and then upload the predictions. The problem is, I mean, the good thing about having something like this, OpenML is kind of a digital playground, right, for algorithms. Yeah? As you can really program on this, you can now, of course, build optimization algorithms and bots, exploring bots that, try out different things, and then maybe even, learn how to do machine learning. And that's really what we are interested in as scientists, right? I mean, of course, we also love reproducibility and openness and so on, and benchmarking, but what we really want to do is do machine learning on the next level, right? Auto-construct algorithms, learn, I mean, kind of encode this gut feeling that we all have here in the room, what works well when, automatically learn that, and give back that information again to the community so we can also analyze this with our human minds and understand this.
Two more examples. This is the runtime prediction bot. So if it sees a data set, it will predict how long each algorithm that knows will need to build a model on that data set. Right? And it does this within a couple of seconds accuracy. It tells you a random forest will take this long, a neural net will take that long, based on all the metadata that it learns from. Another one is the dataset similarity bot. So if you give the data set, it tells you which data sets are similar to the data set that you uploaded, and then maybe you can learn from that.
Do you get these stats like right when you create your project or upload your data?
Can you repeat, please? Yeah. I didn't even.
Exactly. So the idea is
can you repeat the question?
So the question is, will you see this when you upload your new data sets or create a project? Yes. The idea is that right now we have just this page for data sets. There will be bots appearing that tell interesting things to you. So it will tell you which data sets are similar to your data set. It will tell you how long models will take to train on your data set. And it will, if you give it a task, like classification, it will also automatically build models for you. This will appear online.
I mean, another thing that we are thinking on, I mean, this is like one side of the coin where you basically try to automate this as much as possible, have an automatic optimization algorithm, a tuning algorithm on top of everything, but another potential thing would be you upload your data set and then somebody, even without installing R and having available a cluster locally at his facility, could log into the web system and then do some computation or start some computation through the web browser, by maybe connecting to Amazon, or to Azure or something like that. But all of this is not really, I mean, all of these ideas exist and prototypes, non-public prototypes exist for this, but we are not really finished with that.
Do you have like any commercial products yet?
There are some discussions going on at the moment, but the answer is no. So the question was, are we commercial in any sense at the moment? Do we have commercial products built on top of this? And We are exploring certain things at the moment, but not yet.
Not in the short term.
Yeah.
No, this is really meant also to invite other people, right? If you are interested in AutoML, OpenML gives you a lot of tools to do AutoML yourself. So you can write your own bots, you can write your own scripts on OpenML, everything is openly available.
I mean, maybe to add, I mean, maybe you also correct me there, but hopefully I'm speaking for you that I think it's highly, highly, highly unlikely that we will ever kind of sell this system in a year and completely close it down. Yeah? So, I mean, we are scientists and we are really interested in that thing staying open and being a tool for scientists. Yeah? If other people can do commercial stuff with it, the better it is, right? But we will never, I think, commercialize this completely. Yeah.
Yes?
When partitioning your data for cross-validation, do you only rely on the useR package, or are there any other partitioning methods for it, for example, for spatial partitioning?
So the question was, how do we do the partitioning, right? I think when this started out, Joachim,
Well, we have an open backend, right? So
Yeah.
we have everything works against an API. If you want to create a task creation bot, you can do that. And you can use any sampling method that you want to use. What's currently running right now is it's based on, I think, on Weka. And it uses stratified cross-validation to build the trained test beds. But if you don't like that and you want to create your own one, you can write your own task creation bot and let it run on the system.
I mean, we kind of need to we have already generalized this also with regard, I mean, the splitting, I think, is not so difficult, yeah? Because most of this stuff is either supported, for example, already by Weka, which Joachim started out with, or it would not be so hard to program into it. But sometimes it gets a bit harder with the complicated performance measures. Yeah? I mean, certain performance measures for survival analysis and so on, that's much harder to implement correctly, and also you don't want to have any mistakes in there, and this is why we are kind of generalizing these evaluation engines also on the server. Yeah? And then hooking it, for example, either into MLR or Python or scikit-learn and so on. Yeah?
As far as I understand, everything runs locally. Like I run a model in my computer and only tell everyone how I did, but nothing runs in the cloud or anything like that, right?
Okay,
Nothing runs on our server, but a lot of things happens on the cloud.
okay, to repeat the
But it's like a repository more than a computing.
So to repeat the question, is everything, I mean, are the experiments being run locally, yeah, or is anything run in the cloud or on the server? And I mean, yes, right? I mean, at least in the beginning it was like this, but remember the discussion about the bots and so on, yeah, so that we are already doing stuff after datasets have been uploaded, yeah, automatically on our site.
We have also some plans. For instance, if you have AWS credits, we will create an interface for you where you can give your information and we will run stuff on your behalf if you want to. But you can also easily do it yourself.
And the thing is, the more we open up this automatic computation route, I mean, it becomes a question of funding and it also becomes a question of security, right? And we need to get both of these things right, which is not particularly trivial.
The core of OpenML and all of this is that we believe that machine learning will be very important and that it should be readily available to everybody. Right? Also, the AutoML should be available to anybody. It should not be in the hands of a few. So that's why we make everything openly available, because we want to speed up AutoML, we want to increase the proper use of machine learning, and that's what motivates us. And we will keep everything open to empower people to do that.
So the question was whether there's a relationship between models that have been run on different data sets. Is that correct? So can you kind of give us a question you would like to answer when that relation would be there? Yes. Okay. Yes, of course that's possible. To repeat what you said, so you said, let me try to summarize this. So you're asking if I have, for example, a specific task or data set, can I track the development over time and see, well, improvements there? Yes, I mean, maybe you want to open up the usual slide for that with your students. Do you have that? So, of course, I mean, you can track for each task on the web page, and you can also easily do this through the API. You can compare how the models performed, and I mean, after a certain time, you should see an increase there. You can see how people get better and better and better. Joachim, for example, did this with some students in his class, and then you can see a curve over time where students look also what the other guys did yesterday or last week, and then they're saying, well, that already works well, but maybe I can, I don't know, do some dimensionality reduction before I go into the model, and then it becomes even better, and sometimes they are right and sometimes not, and you can track this over time and look at this. And even, I mean, of course, because you can peek into each individual experiment, you can also get an intuition about, well, why that maybe worked well or not, yeah? Because you can see, for example, maybe I did something yesterday and that created a huge increase in performance, and then you can look into my experiment and see what I did. Yeah.
Yeah. Just to show it's possible. This is not OpenML right now. This is something we want to work towards together with Balázs Kegel in Paris. So he has done this very nicely. So here you have students. So every dot here is a model uploaded by students. And so on the right, the blue lines means people looked at your solution. Red lines mean you looked at other people's solutions. So for any student in this area, for any solution, you can see who looked at whom and who looked at one and who credited other people's solutions. So if you think there's a great solution, I'm going to credit this person. This is also noted. It's a very nice approach. And you can also do analytics. On the left, for instance, you see how you can identify early influencers, people who write very good models early on. You can see people who follow along, and you can see inventors who come up with radically new approaches to work very well. So all this kind of analytics will be great for the classroom, and this will be possible with this collaboration.
Shall we move on? Where are we time-wise now? So 3 o'clock. Can you open the slides, maybe? Yeah, I'm going to use that one here. I'm going to switch it. Okay. So time-wise, I mean, we are now at 3 o'clock. I would guess we maybe need, without the practicals, maybe another hour, 45 minutes, something like that. So we will just go on now. Okay? Okay with you? Or do you want us to stop at 3:30 for the global break? Yeah? We don't necessarily have to, so you can decide. We'll just have a break at 3:30, okay? Yes, of course, yeah. So we'll stop at 3:30. I'll make sure. If I don't, just shout at me, okay? Sometimes I forget. So Joachim has now told you how to use the basic OpenML functionality, yeah? List stuff, figure out what you maybe want to work on, how to download this, get this into R, and then extract the meta information and extract the data, and then you can work on stuff. What I now want to do is give you a short introduction to the MLR package. That's something I have created before OpenML existed, so that's our umbrella machine learning package in R. We are about 8 to 10 persons developing that, and have quite a few contributors now. If you're interested in the project, so I'll just give a rough outline of the whole thing in maybe 15 minutes, where I can only cover a few glimpses of what the package can offer to you. If you're more interested to that, just go to this URL here that takes you to our GitHub page, and there's an extensive online tutorial there. You can see who is actually coding with this. You can ask questions about this in the GitHub tracker, yeah, and figure out how the package really works. Yeah, okay, there's another line of installation on the slide for the upcoming practicals, where I have mainly chosen to work with a random forest and an SVM, but yeah, that's useless as all of the other stuff we had before, where you need the network. Also, MLR currently is a dependency for OpenML to make some things work, but you don't necessarily have to use it when working with OpenML. It just makes running algorithms super easy, and this is why we are showing this to you. If you don't know the package, what's it about? So it's a general package to handle quite a lot of machine learning tasks. So it can handle classification, regression, survival analysis, clustering. We can do pretty general cost-sensitive learning, multi-label classification, and we are even extending this over the next 6 months into various other tasks. Yeah? At the moment, we are already supporting more than 160 basic learning algorithms, and maybe there should also be a quote around basic, because one basic algorithm, I don't know, is the SVM function from KernLab, which contains, I don't know, 20 different variants of support vector machines through one interface. There's a unified interface in the package for basic building blocks like tasks. So we are also using tasks in nearly the same manner as OpenML. So tasks is again data plus meta information, what you should predict and how this should be measured. There's, learning algorithms, and that's maybe a bit different than other similar packages in R, where we are maybe closer to stuff like scikit-learn in Python. So also learning algorithms are objects, and these objects again contain meta information that you can use, you can query, you can work on, and for OpenML specifically, you can upload. So we know what goes on inside of these algorithms. We know lots of meta information about parameters, we know lots of meta information about properties, and that kind of, I would argue, goes hand in hand with OpenML, where you then want to auto-extract this information and upload this to the server. Third component is resampling, so cross-validation splits, also objects, and hyperparameters. So there's even a little language just to be able to talk about hyperparameters and parameter sets, which becomes really handy for tuning. And like I already said, so we have a little reflection system going on where nearly all objects are queryable. So you can ask them what they can do. Can they handle missing values natively? Can they support multi-class classification, blah, blah, blah. All of that is stored inside of these learning algorithm objects. And then we have these generic, basically support this generic schema here where data or the task is split up into a training and a test set. You run an inducer. The inducer induces a model. If you put new data, a test set into the model, you get, of course, predictions. On the predictions, you run various performance measures, and you get out performance values. And if you repeat that in a loop, you basically get resampling, like cross-validation. The whole thing is at the moment programmed in S3 because R6 didn't really exist at that time when this was created. Actually talking a little bit about migrating this to R6 over the next couple of months, which would be a tremendous amount of work. So this is not really done yet. And this object-oriented perspective of the package makes it, I would argue, also quite easy to extend it in various ways. Most of the structure in the package works exactly the same way, so parameter tuning, feature selection, and so on works completely the same for all of these different tasks here. You implement it once and can use it in many different ways. On a basic level, how can you train and predict and measure performance? How can you basically do these things here without the loop, without the resampling loop? So the first step is you, like on OpenML, you create a task, you input a data frame, you specify a target variable that gives you an object, and the object, as you can see, already collects quite a lot of information about what goes on in that task. So you have a name, you have the target variable, you see the number of observations, how the feature type distribution looks like, whether there are numeric or categorical features in there, whether we have missing values, can associate weights with the observations, blocking, not really going into that now, how the class distribution looks like, and positive classes for ROC analysis. Second component you always need to construct is a learning algorithm. So you call make learner. It's all pretty usual OO way. You call a constructor. Here you choose a certain algorithm in this instance R part, which is just a card tree, a card decision tree. You can cite hyperparameters, which will also be stored in the object. And again, you get a nice little printer that's where you can see that lots of information is contained in here. Most importantly, the package that's auto-loaded. You can see all of these properties here that I already talked about. So, for example, by looking here, you can see my mouse, right? You can see that the decision tree, of course, can natively handle missing values through surrogate splits, so we know all of that stuff. And there are predict types where you can either predict discrete class labels or probabilities and other stuff. And here you have the hyperparameter settings that you can change as user and later on also tune over. And if you train that type of thing, it's always the same API, call the train function, input the learning algorithm, input the task, and you can also specify a subset if you don't want to train on everything, but just a specific index set. So here I'm training on iris, I'm just taking every second observation, yeah, so 1, 3, 5, and so on. And I'm getting back a model that's just a thin layer around the usual RPART model that is fitted by the RPART package where we of course just call into that. Prediction, also not very surprising. Take the model, take the task, take a subset, and also input some new data frame. You get back a prediction object, which is basically an S3 object wrapped around the data frame. You can see the truth column, the response, the IDs from the tasks, so which observations the predictions refer to, and we measure also stuff like times and thresholds for probability predictions and so on. And the last basic function, of course, is figuring out how well this worked. So on the prediction object, you can call the performance function, and you can input any combination of performance measures. So in this case, the misclassification error, the mean misclassification error, or here I also have the balance error rate. So they're pretty short abbreviations for these measures. You can either, if I would have network access, I could now go to the tutorial and show you a long list of these measures and tables. But you can also do this from inside of R. You can list all of the objects there. You can list all of the learning algorithms. You can list all of these measures. And all of the information that's in the tutorial is actually in these objects because we auto-generate our documentation from this machine-readable information. Can you speak up a little bit, please?
What does the RPART package do exactly?
The RPART package, so that is short for recursive partitioning, and this just means it's a card tree, so a classification and regression tree, you know, where Breiman wrote the book about 1984. Yeah? It's just the card variant of the decision tree. Yeah? I'm just choosing that as an example because A, it's super fast, and B, it usually is installed with every R installation. Yeah? So and everybody knows a decision tree, I would assume, in machine learning. Yeah? This one?
Yeah, you predict on the model and the task. Why do you have both? Doesn't the model, why do you need the task? Doesn't the model have the task? Actually, it's just a very silly question. Is there a particular reason why the model doesn't have the task?
Okay, so let me repeat this. So the question is, why do I have to input the task here as an argument? Yeah. It's not a silly question, but of course we don't want to store the data, the complete data set inside of the model. I mean, some packages in R actually do that, and I hate that every time I see that because it wastes lots of memory, right? So this is, I mean, the new data that you predict on. I mean, there are two ways you can use that. Either you kind of have collected everything on the task, and then you just train on certain subsets of this. This is what I'm showing here. Or this is mainly during model selection, right? When you evaluate how certain algorithms work, and later on when you deploy this, there might be just a data frame without a response column, without a target column, and then you can use that as well. Yeah? Then you say new data equals, I don't know, my new data frame.
Is MLR required or support other frameworks?
It's not required in this, like that you cannot use OpenML without it. I mean, Joaquin showed this to you. You can download everything. It just makes it a lot more convenient and to run algorithms super quickly with one command. Yeah, but you could integrate anything with that. H2O is integrated in MLR, so yes. Yeah. So you can call. I mean, you can say, I don't know, classif.h2o GBM or whatever. Yeah, and then you can run everything from H2O. And if you have a commercial license, you can even run it in parallel for H2O.
What are the possible measures here? Where do we find the list?
In the online tutorial. So for all of the things that are supported, you just need to remember this here. Go to the GitHub page when you have internet again, and then you follow the link to the tutorial, and in the tutorial there's an appendix, and the appendix lists all of the supported learning algorithms, all of the supported measures, all of the supported, I don't know, filtering and feature imputation methods, yeah, everything that's large and we can list. The slides will be available on 2 platforms. So we gave you a bit.ly URL in the beginning. That's also here. So just after, maybe after the talk, come to the front and write it down. And you can download everything there. So the idea was that you could have also done this in the beginning with network access. And we were also asked by the organizers of the useR to hand in our stuff to the official useR webpage, which we will do tomorrow. So you can also download it from there. But I would suggest to write down the bit.ly URL. These slides will be on there. Joaquin's extra slides for the OpenML background will be on there, and some third element. The cheat sheet is also on there.
I will also put a link on the main OpenML page. OpenML.org, you will find the link to all of this.
That's a very good idea. Oh, okay. It's pretty mature, and it's kind of, what? Oh, sorry. So the question was, can MLR support time series? And I think you are referring to time series forecasting, yeah? So forecasting into the future. It's pretty mature because Steve worked on this for, I think, half a year, and our main problem at the moment is not, well, the maturity of it, just like rereading everything and checking it so we can like officially merge it into the package. So we have quite a complicated merge process because we really care about unit testing and code quality. So that takes some time, and I think at the moment Steve is getting a little bit angry about me that I didn't do this 2 months ago. But we are very, very close to merging that in. And we will also support another thing, which is functional data. So this is where time series are features. That's also pretty far advanced. And anomaly detection. These will be the 3 big things task-wise that will be merged in pretty soon. Okay.
Carrot. How's it different? Haven't used MLR, have used Carrot. Just curious.
Okay, you are asking the generic question that I always have to answer. So how does it compare to Carrot? I would say, well, I mean, on a feature level, I think it's quite comparable, yeah. So many things that we can do, Carrot can do, and the other way around. And then there are some specific things where we are better, where I'm not sure whether in both directions that matters so much. So I would, for example, we have Bayesian optimization in there for hyperparameter tuning and other stuff. And in some other areas we have a bit more, and I think in feature selection and filtering, Carrot is a bit stronger. The main difference is, I think, this OO design, yeah. Very, very clean, object-oriented design, which is much closer to scikit-learn, yeah. Where you can, and I mean, the other thing is, I mean, and I think this is kind of the underlying reason is that, I mean, Carrot supports classification and regression. We support all of these other things, plus maybe these 3 extra tasks that will become available. And this is because the underlying object structure is so generic and the same. Yeah. And yes, in my case, yeah. In our case, yeah. And I don't think that Carrot will do that very soon, yeah. Or I don't know. And you would have to ask Max about that. Yeah. Okay, the question is, how is pre-processing being done in the package? Okay, that's a pretty complex question. Okay, I'll try to answer this as brief or as well as I can do in a very limited amount of time. So first of all, of course, some algorithms in R already support pre-processing. Yeah? Some do scaling of the data and other stuff, and that's then naturally supported. At the current stage, we allow certain so-called wrapper mechanism where you can wrap around other things around your algorithm. That's really nice, in my opinion, that you can kind of take a basic MLR algorithm and then put pre-processing around this. Yeah? Either predefined pre-processing, filtering, imputation. or custom pre-processing code, where you take a chunk of code and say, in front of every MLR learning algorithm that I wrap this around, I want this, I don't know, custom PCA type of thing being run. Yeah, I will also show you one other cool thing that we are currently doing in Google Summer of Code in a few minutes that I think will really answer your question, yeah, in a much better way. But we support quite a lot already. Yeah. Okay, I'm getting a little bit. 20 past, so I have 10 minutes left, so okay. We covered that. Now resampling is also super easy. So for resampling, I would say that we suggest really most of what is out there: cross-validation, subsampling, different bootstrapping variants, stratification. I think most of what you need is there. Of course, just normal train test splitting. And the normal way to run this, again, you create the learning algorithm, you know how this works. Then you create a description object. Again, everything is an object, so you create a description object for cross-validation, CV for cross-validation, iterate for the number of folds. There are also predefined objects in there, so CV2 you could use instead of this longer line here. And then you call the resample function. The resample function takes the learning algorithm, the task, again, this resampling description here, and that basically tells the algorithm to run a two-fold cross-validation on the task, and again measure misclassification error and balanced error rate. And if you want to, you can also store the complete models if you want to look at them later. If you don't do this, you will only get prediction and performance measures. And that thing then returns a container object that contains obviously these performance values, also the performance values per resampling fold, the predictions, and the models if you're requesting that. There are various shortcuts in the package how to even write this more concisely by just saying, I don't know, crossval or whatever, which are abbreviations for the general resample function. And here we are peeking now again into the, we are peeking into the container object, this R thing here, where you can see these performance values or the performances on the different splits. So in this case, we were running a two-fold cross-validation, so we have two measurements on test sets. You can also request measurements on training sets. By default, they are switched off. And you can also have a look at the complete prediction object, which contains truth and responses. And then you can do, I don't know, some kind of a residual analysis on this, or do a more fine-grained analysis of the y's and the y hats. And here you can see, because I was requesting that specifically, I get all of the models from the cross-validation. For efficiency, by default, this is switched off. If you want to run multiple models on one data set, or maybe even multiple models on on multiple data sets, there's again a little syntactic sugar, the benchmark function that takes a list of learning algorithms, potentially a list of tasks, a resampling object, and that will run every learning algorithm on every task, and store the results, again, in a very large container object containing all of the predictions, all of the performance values. And of course, you can parallelize that. MLR has a very nice way of parallelizing things by going through a pretty flexible aggregator package, so parallel map and batch tools, which means you can run this on multi-core systems, you can run this in socket mode on MPI, and because we also support batch tools, you can run this on, I don't know, Slurm, Sun Grid Engine, whatever cluster you have available, with just adding one line of configuration, and you can also control the level of parallelization. But now I'm kind of getting a little bit off track and taking up too much time. So this function is important. I mentioned this here specifically on the slides because OpenML uses this benchmark function to run experiments together with MLR. So what you produce internally are these benchmark objects. Here is a longer list of other features that I couldn't really talk about. So we have different NA imputation techniques in there and a generic system for that, different feature filtering techniques, imbalancy correction like SMODE, to oversample the smaller class in a more intelligent fashion. This is something that I really like about the package, that I really wanted to have in there. Let's put it that way. You can really extend learner functionality by wrapping it with other stuff, pre-processing, multi-class to binary reduction algorithms. You can extend stuff that's missing in the basic learning algorithms, make them powerful, and you get make them more powerful, and get back objects that behave in the same manner API-wise as the basic learning algorithms. We of course also, we support nested resampling, yeah, so by adding tuning to an algorithm, you can now resample that auto-tuned algorithm and get nested resampling also easily. That's one line more code. You don't have to code any extra loops. I'm pretty interested in efficient tuning and black box optimization, so we also support Bayesian optimization. I'm not sure whether you've heard about that. It's one of the most popular methods at the moment to efficiently tune machine learning pipelines. That package we have also written. That's MLR MBO for model-based optimization. That's also now on cron. And there's a little paper on arXiv about that, and we also support iterated F-racing from a group here in Brussels, which is, I think, not present here at useR. You can even do multi-criteria optimization, also Bayesian multi-criteria optimization, feature selection, ensembles, bagging, stacking, and so on. And these are the things which will come next, which I think I already talked about. So anomaly detection, functional data handling, and time series forecasting. That's on the top of the list at the moment. And a little teaser, we are pretty active in Google Summer of Code each year, or try to be, if Google allows us that, and the R Foundation. This year we have one project, and I'm getting extremely proud of this project because what Martin Binder, our student, is doing looks extremely cool already after just a few weeks. Hope you can read this. If not, there's also a little pull request that has in the title CPO, and CPO is for composable pre-processing operations. Maybe a nicer term would be efficient, beautiful pipelining. And you can see here, I can with this new system, you cannot do this currently with MLR, only hopefully after GSOC. You can say something, yeah, create a pipe where I'm doing median imputation first, then I'm dropping every constant column in my data set, then I'm doing a PCA, and then I'm doing feature filtering with gain ratio. And now I can take this pre-processing pipeline, put it in front of a learning algorithm, and get something pretty complex. And these things behave like learning algorithms. They can be trained on data, and they can be applied on new data. They have hyperparameters. This pipeline has actually quite a longer list of hyperparameters, and you can tune this. Yeah? And I can add 5 more lines to this, and then I have Bayesian optimization running on top of this, which I find quite cool. And you can even do stuff like multiplexing, where you say, okay, I want to do this, either that pre-processing or that, or feature unions, so do that pre-processing, that, and that, and that, and then join it all together. Yeah? If you're interested in that, there's even a little preliminary vignette where Martin explains what he can currently do and what are the next steps. This should be done in October, and because, well, that's the end of Google Summer of Code. Now, not back to OpenML, but let's have a break, right? Yeah, of course, we will continue. I mean, we have a second slot anyway. This was planned for 2 times 90 minutes.
Please come back.
Please come back. There's a second session. A regular second session for this one here.